Okay, so now we're going to shift to doing hypothesis tests about a claim, about a mean mu. So again, we're going to have a null and an alternate hypothesis. Someone's claiming what the population's mean for something is, and that's our mu. So they might be claiming that the mean is equal to something, or they might be claiming that it's more than something or less than something. Okay, but whatever the original claim is, we have to turn it into the null hypothesis is that the mean is equal to something, some number, and then the alternative hypothesis is that it's less than, or it could be greater than, or it could be does not equal to the same thing. These two numbers, it's the same number put here and here. And then we also set a level of significance, again, either 0.05 or 0.01 or something like that. We then do the sample. And now the sample is we take a simple random sample and we measure the thing we're talking about, and we get the sample mean. So that would be one number. And we also want to, along with it, get the standard deviation, because that's going to matter. Okay. Now, that's the data, and we want to see how well that data lines up with the null hypothesis. Now, when you're doing it manually, you would put your x bar, the null hypothesis mu value, and your standard deviation and n right here and here, and you compute that, and then that number has a t distribution, which we've seen before, and you look it up on the t chart with degrees of freedom n minus 1, and you turn that into a p-value. Okay, so that part is what's different for a mu. Okay, but then the rest of it is the same. You interpret the p-value by judging it, by comparing it to your alpha. And once again, if your p-value is less than alpha, then statistically significant, you reject the null hypothesis, because that means getting this data in a world where the null hypothesis is true was really unlikely, but you did, so maybe we don't live in a world where the null hypothesis is true. Okay, so you reject it. Otherwise, if the p-value is bigger than alpha, you don't reject it. Okay, we're going to do an example in just a second. But if you're not doing it manually, then this is the t-test on your calculator. So we've done the t-interval when we're doing a confidence interval for mu. This is the t-test for when we're doing a hypothesis test for a claim about mu. And again, before doing the example, let me just go through the requirements for the t-test to be appropriate. Number one, as always, your data should be coming from a simple random sample. And the second one is, it's basically the central limit theorem requirements, which is you have to somehow already know that the population that you're talking about has a normal distribution, or if you don't know that, you need your sample size to be at least 30, because then the central limit theorem kicks in, and you get to say that x bar is normal even if the original population is not. So let's do our example. So a scientist makes a claim that tornadoes travel 2.5 miles on average before they dissipate. So a tornado is spawned, and it moves through the land, wreaking havoc, and then it kind of goes away. And the scientist, you hear a scientist make a claim that it usually goes around on average 2.5 miles before it breaks up and disappears. But let's say you think the mean is more than that, more than 2.5. You think that he is wrong. Okay, so the setup would be, null hypothesis is that the mean is 2.5, because again, null hypothesis always has to be equals, and the alternative hypothesis is that it's more than 2.5. And again, you set your alpha. You're always supposed to set your alpha before you start analyzing your data. It's cheating otherwise. All right, so now you get your data. Sample of 500 random tornadoes. And so actually, this is some data that's in our book. So here it is in StatCrunch. And so I can do stats, and I can do the length. By the way, there's 500 tornadoes here, a random sampling of 500 tornadoes. One of the columns is the length, how long it went before it disappeared. I want mean and standard deviation. and then I'll hit compute. And so the mean is 2.72, 2.724. All right, so my x bar is 2.724, and my standard deviation is 6.609. So the mean definitely is more than 2.5. Is it so much more, though, that this, like in a sample of 500, it would have been pretty hard to get 2.724 if the real mean was really 2.5. It would have been possible to get a sampling that was just on average higher than what it sort of should have been. That's the question, right? And that's what our distributions and our p-values will tell us. One thing is the standard deviation is pretty big, and if you look back at the data and you look at these lengths, what you see is some of them are really big, and then some of them are really small. So there's a great variation here, and that's reflected in the standard deviation being pretty large. Okay, so if we go to our calculator and we do a t-test, now remember, just like with interval, on the t stuff on your calculator, you're going to have the option to do data or stats. Now in this case, we have the stats. We have the x bar and the s, and n is 500. So we're not actually entering in the raw data, but that's the other option that you can do. Okay, so we put in, we go to t-test, we put this into our calculator. Okay, and I am getting a p-value of 0.224. So yeah, again, this is not too small, and it's bigger than 0.05 for sure. So there was a 0.224 probability of getting 500 random tornadoes with stats like this, or more, or further away than 2.5, if the mean really was 2.5. So it's plausible. It's not crazy that that could have happened. It's not so unlikely that we're questioning the claim that mu is 2.5. All right, so it's not statistically significant, and we do not reject the null hypothesis. That's our conclusion. The mean could be 2.5. We haven't found enough evidence to overturn that. We're not saying it definitely is. Notice we don't say we accept the null hypothesis and case closed. No, it's just we don't have enough evidence to reject it at this time. We did get something higher than 2.5, but it's just not far enough away that it couldn't have been 2.5. Okay, let's do another one. You want to test the claim that female supermodels are taller on average than the general female population, whose mean, let's assume we know, is 162 centimeters. Okay, so the mean of 162 centimeters, are female supermodels taller on average than that? Right, so the null hypothesis would be that the mean for supermodels, so mu here is mean for supermodel heights, is 162. And the alternative hypothesis is that it's more, right? And maybe we suspect that it is the latter, that it's more. But remember, your null hypothesis is always the one with equals. Okay, and again, 5%, I'm just keeping that the same, but remember that could change, and in a problem from the book or on a test, you can be told what that is. In real life, you have to decide that ahead of time, depending on how conservative you want to be. The smaller this is, the sort of more conservative you want to be. You don't want to make a mistake and reject the null hypothesis falsely. Okay, so we do a simple random sample, and we have 16 female supermodels. It's not a huge population, I guess, but maybe all supermodels from all time, and we take 16 of them randomly and we get their heights, and here they are in centimeters. And, you know, just glancing at it, your gut might tell you, oh yeah, these are all pretty big compared to 162. Not one of them is less than 162. But again, remember that maybe, you know, this is not a huge sample, and maybe this could have happened just by chance, even if the real mean is 162, even for supermodels. Maybe, but also maybe your gut's telling you probably not. This seems pretty convincing. But let's see what the test tells us. All right, so now this is a case where we have raw data. So we can put it into our calculators in a list and then have our calculator do everything from scratch. It'll give us the X bar and the S, and it'll do the test for us. So you have to type this into your calculator in the list, and then go over to the t-test and tell it to look at that list, right? Similar to how we did it for confidence intervals. All right, so we do that, and I'll pause and come right back with the results. Okay, so the mean for this group is 177.25, as expected, definitely bigger than 162. And the standard deviation isn't that big. These numbers aren't varying that much. It's only 1.84. And so my calculator gave me that, and it also gives me my p-value, which is 9.78 e minus 16, which means times 10 to the minus 16, right, which means a 0 and then 15 zeros and then 978. So for all practical purposes, 0. It is astronomically unlikely that supermodels' heights could have the same mean as the regular general population of 162, and us getting 16 randomly selected people whose average is that big. It's just too unlikely. It's as impossible as things get without truly being zero probability. So this one is statistically significant. And we do reject the null hypothesis. We do reject the claim that the mean is 162. We go to the claim that it is more than 162. We don't know what it is. You know, we could do a confidence interval with this data to get a range for what it might be. But what the test has concluded is that it's probably not, that it's not 162, that it is more than 162 at least. Okay, so this is how a hypothesis test for mu works.